Good evening, everyone, and welcome to another journey through the wonders of our remarkable planet. Tonight, as you settle into comfort wherever you may be listening, we're going to explore one of Earth's most powerful and enduring forces. Picture, if you will, the ground beneath your feet right now. Solid, reassuring, permanent, yet beneath that stability lies a restless energy that has been shaping our world for billions of years and continues to do so at this very moment. If you are enjoying what I do here, I hope you'll consider subscribing to hear more stories like this one. Also, I'd love to know where in the world you're listening from and what time it is for you. Naturally, we're discussing volcanoes, not in the dramatic disaster movie sense though. Rather, we'll learn how these geological wonders are the silent creators of life itself, toiling diligently in the background to establish the very circumstances that enable our existence. The question for tonight is straightforward, yet profound. What if volcanoes continue to shape our planet? They haven't stopped, which is the lovely truth. They won't. Take a moment to close your eyes and visualize our planet from 4.5 billion years ago. There are no oceans full of life, no continents as we know them, and no atmosphere that is fit for human habitation. In its place is a molten ball of metal and rock that is slowly cooling in the frigid vacuum of space. The mountain peaks we imagine today were not the first volcanoes. They were huge open wounds in the surface of the Earth that let out the gases and heat from the planet's interior. Something remarkable was accomplished by these ancient volcanic processes. They started forming the air we breathe now. Water vapor from volcanic vents is present in every breath you take, the carbon dioxide that photosynthesis in plants converts to oxygen. Those early eruptions were the source of much of it. In addition to sculpting the landscape, volcanoes created the air that is in your lungs as you read these words. By our standards, the early Earth was a violent place, but life was made possible by this very violence. If it were possible, picture yourself standing on that ancient world. You would see a landscape that is continually changing due to volcanic activity. Ash clouds rising into the thin atmosphere, lava flows reaching the horizon, and the unceasing rumble of a planet discovering its geological rhythm. Volcanic outgassing during this time, referred to as the Hadean Eon, started to fill the first ocean basins with water vapor that condensed as the planet cooled and gradually thickened the atmosphere. By human standards, this process took hundreds of millions of years. On a cosmic scale, however, it was extremely effective. In essence, our planet was teaching itself how to support human life. Additional water and organic compounds were added by the early period's bombardment of asteroids and comets. But volcanic activity provided the stable base that prevented these contributions from just boiling away into space. Early Earth would have remained frozen and unable to sustain the liquid water necessary for life if it hadn't been for the greenhouse gases emitted by volcanic activity. However, let's go ahead in time to a point when our planet had started to stabilize a little. The earliest simple life forms emerged in the oceans of Earth some 3.5 billion years ago. These were small, single-celled organisms rather than the sophisticated beings we see today. And here's something amazing to think about. They probably wouldn't have been possible without volcanic activity. You see, early life required energy sources, minerals, and nutrients that were mostly hidden in solid rock. By grinding up the Earth's interior and supplying vital elements like sulfur, iron, phosphorus, and potassium straight to the emerging biosphere, volcanoes served as nature's pharmacists. Some of the earliest communities of life were formed by hydrothermal vents, which are underwater volcanic vents. They produced warm, mineral-rich water that was ideal for the evolution and growth of early organisms. Volcanic gifts were not passively absorbed by these early life forms. They took an active role in changing their surroundings. Chemosynthetic bacteria that could break down the sulfur compounds erupting from volcanic vents were among the earliest living things. Others discovered how to use iron that had been dissolved in seawater, which allowed them to gradually remove it from the oceans and deposit it in enormous iron formations that are still visible in ancient rocks today. We are still learning about the symbiotic relationship between early life and volcanic activity. Chemical cycles were stabilized by life, which improved the conditions for even more complex organisms. Life supplied the organizing principle that progressively turned a disorganized chemical soup into ordered, self-maintaining ecosystems, while volcanic activity supplied the energy and raw materials. Deep in our oceans, volcanic vents continue to carry out this age-old function tonight while you sleep. These geological fountains of life are surrounded by communities of strange and beautiful creatures that live miles below the surface, where sunlight has never reached. These volcanic oases are home to giant tube worms without eyes, ghostly white crabs, and bacteria that prefer to eat chemicals rather than sunlight. They serve as tangible evidence that volcanoes still play a vital role in supporting life today. Our knowledge of the potential for life was completely altered in the 1970s by the discovery of these deep-sea volcanic ecosystems. When researchers on board the research submersible Alvin visited the Galapagos Rift, they discovered something that, based on our understanding of biology, shouldn't have been there. Large, sophisticated animal communities were flourishing here, living in total darkness and being powered solely by the chemical energy emitted by volcanic vents. The enormous tube worms they discovered, some of which were as long as 8 feet, lacked any digestive systems, including mouths and stomachs. Rather, they had symbiotic bacteria inside their bodies that produced organic compounds from hydrogen sulfide and other volcanic chemicals. These worms were living, breathing examples of chemosynthesis, which is the process by which chemistry, not sunlight, powers life. However, the tube worms were only the first step. Ghostly white crabs with bodies adapted to the crushing pressure and toxic chemistry of the deep ocean were discovered by the explorers scuttling across the volcanic landscape. Some fish had lost their eyes completely and were able to navigate in the never-ending darkness by smell and vibration, while others had enormous eyes that were designed to detect even the smallest bioluminescent signals. Most astonishingly, they discovered bacteria that were directly residing in the lead-melting water that was evaporating from the vents. By surviving in environments that would immediately kill most organisms, these extremophile bacteria pushed the limits of what we thought was possible for life. They proved that life is much more resourceful and adaptive than we had thought. Beyond marine biology, these findings had significant ramifications. Perhaps life could exist in equally difficult environments elsewhere in the universe if it could flourish in such harsh conditions on Earth. Suddenly, the moons of Jupiter and Saturn appeared much more promising as possible habitats for life because of their subterranean oceans and potential hydrothermal activity. Approximately 250 million years ago, all of the continents of Earth were compressed into a single supercontinent known as Pangaea. Consider a world map where there is only one massive landmass and one huge ocean encircling it. One of the most important volcanic events in Earth's history started to take shape during this period, but it happened so slowly that anyone watching would have needed the patience of geological timescales to notice. Something extraordinary was simmering beneath the surface of what is now Siberia. Magma started to emerge from the Earth's interior in huge, gradual floods of molten rock rather than in violent explosions. Layer after layer of volcanic rock, some deposits reaching heights of several thousand feet, would eventually cover an area larger than Europe, with what geologists now refer to as the Siberian Traps. This was no ordinary eruption of a volcano. This was more akin to Earth gradually leaking lava over a vast region over millions of years, rather than the spectacular explosions we typically associate with volcanoes. It had a significant effect on the environment. Huge volumes of sulfur compounds, carbon dioxide, and other gases poured into the atmosphere, drastically changing the chemistry of the oceans and the climate of Earth. It is nearly impossible to imagine the size of the Siberian Traps. The amount of lava that erupted was sufficient to create a layer of rock that was almost 1,000 feet thick over the whole continental United States. However, the duration of this event was just as important as its quantity. An estimated 40 trillion tons of carbon dioxide were released into the atmosphere during the nearly 2 million year long eruptions. The climate change that resulted was disastrous. Ocean acidity sharply increased, ocean acidity sharply increased, global temperatures skyrocketed, and oxygen levels fell. Oceans became stratified, separating deep water that was rich in hydrogen sulfide from oxygen-rich surface water. Entire ocean basins were covered in dead zones as a result of massive algal blooms that ate up the available nutrients. It was just as bad on land. Large swaths of vegetation and soil were contaminated by acid rain. Few organisms could survive in the conditions caused by the combination of intense heat, poisonous gases, and upended food chains. Even insects, which are typically among the most resilient of creatures, experienced massive extinctions, forests perished, and lake ecosystems collapsed. This led to what is sometimes referred to as the Great Dying, the most catastrophic extinction event in the history of our planet. Approximately 70% of terrestrial species and 96% of marine species disappeared. More than at any other point in its history, life on Earth approached extinction. It took millions of years for biodiversity to recover from this volcanic disaster, according to the fossil record. The amazing thing about the history of our planet, however, is that this seeming disaster served as the impetus for the subsequent significant phase of life. Ecological niches were freed up by the extinction, allowing new life forms to diversify and evolve. The seemingly destructive volcanic activity also created new habitats and improved soils. Dinosaurs started their incredible journey to become the dominant land animals for the next 165 million years following the Siberian traps. Life's remarkable inventiveness and tenacity are demonstrated by the recovery from the Great Dying. There was little competition and plenty of opportunities for the few species that survived the extinction. Small, flexible animals quickly diversified into new ecological roles after inheriting the planet. The progenitors of mammals, dinosaurs, and numerous other groups that would rule future ecosystems were among the survivors. In the post-extinction world, the archosaurs, a group that included crocodiles and early dinosaurs, were especially prosperous. They were able to take advantage of the numerous unused ecological niches created by the extinction thanks to their effective metabolism and flexible body plans. Throughout Earth's history, this pattern of biological innovation following volcanic disruption has recurred. Volcanoes build up as well as destroy. They start some stories, but they finish others. It serves as a reminder that creation and destruction are frequently two aspects of the same cosmic process. Additionally, the Siberian traps show how volcanic activity functions on a scale that is much larger than human comprehension. The most significant volcanic episodes in Earth's history frequently take place over millions of years, despite the fact that we typically think of volcanic eruptions as short, dramatic events. They change the course of evolution itself, reshape entire continents, and modify global climate systems. Speaking of building up, let's discuss how volcanoes actually create the terrain that we walk on. Rocks found on every continent were once molten magma from deep within the Earth. Volcanic processes are responsible for the rich soils of agricultural valleys, the granite underpinnings of mountain ranges, and the precious metals that we mine. Volcanic activity is closely linked to the process of continental formation. At convergent plate boundaries, where oceanic plates slide beneath continental plates and melt, magma is created that rises to form volcanic mountain chains. This process produced the majority of the continental crust that we currently stand on. An excellent illustration of this process is found in the Andes Mountains of South America. The chain of active volcanoes that runs the length of the mountain range is fed by magma created by the melting of the Nazca Oceanic Plate as it slides beneath the South American continent. This process has produced some of the world's richest mineral deposits and one of the longest mountain chains over millions of years. California's Sierra Nevada mountains have a similar tale to tell. Deep under old volcanoes, the granite peaks we see today were once magma chambers. The volcanic rocks above were worn away by erosion over millions of years, revealing the crystallized magma chambers underneath. With its recognizable granite cliffs and domes, Yosemite Valley is basically a cross-section of an old volcanic system. You can actually observe this process taking place in real time on the island of Hawaii. The Big Island is still expanding and forming as a result of volcanic activity. Lava flows add new land to its shores every day. Hawaii is a baby, geologically, having formed less than 1 million years ago. However, it already sustains a variety of ecosystems that grow on volcanic soil, including alpine deserts and tropical rainforests. We can learn a lot about the creative potential of our planet from the Hawaiian Islands. Unlike most mountain ranges, they were not created by the collision of tectonic plates. Rather, they originated from a hotspot located deep within the Earth's mantle, which is a column of rising magma that has been largely motionless for millions of years as the Pacific Plate slowly moves across it. Picture a cosmic printhead that is gradually erasing islands from the ocean floor one at a time. After millions of years of erosion, the oldest Hawaiian islands in the northwest are now merely underwater mountains that are gradually receding back into the ocean. To the southeast, new islands are still forming. Loihi is a new Hawaiian island that is currently forming. It is still underwater, but is gradually rising to the surface. A chain of islands and seamounts that spans thousands of miles across the Pacific Ocean was formed by the Hawaiian hotspot, which has been active for at least 85 million years. The Pacific Plate's movement over geological time is chronicled by the Emperor Seamount Chain, which includes the Hawaiian Islands. Like a geological roadmap etched in volcanic rock, you can read the direction and speed of the plate. This serves as a reminder of how patient our planet is, often too slowly for us to directly observe, but sometimes dramatic enough to captivate our attention and awe. The same processes that produce the landscapes we know and love are still at work today. Tonight, from where in the world are you listening? Wherever you are, volcanic activity has shaped the surrounding landscape at some point in Earth's history. So I'd love to know. Though it occurred long before humans, let's focus on one of the most significant volcanic events in human history. A huge eruption took place in what is now Indonesia some 74,000 years ago. More than 670 cubic miles of rock, ash and pumice were thrown into the atmosphere by the Toba supervolcano's explosive eruption. That's enough material to cover the entire state of Texas with 3 feet of volcanic debris. To put things in perspective, one of the biggest volcanic eruptions in Earth's recent history was the Toba eruption. Lake Toba, which is 62 miles long and 19 miles wide, is the caldera it left behind. However, Toba's worldwide influence began with the local devastation. As the Toba ash spread around the world, it blocked sunlight and caused the climate to drastically cool for a number of years. According to some scientists, early human populations may have been on the verge of extinction due to the severity of this volcanic winter. It's possible that our ancestors, who had just started to leave Africa, were reduced to a few thousand people dispersed throughout the world. Genetic studies that demonstrate that all modern humans are descended from a relatively small group of ancestors who lived around this time provide evidence for this population bottleneck. In contrast to other primate species, human populations exhibit little genetic diversity, which implies that our species experienced a severe population contraction not long ago. For early humans, the Toba winter would have been an extremely difficult period. Large-scale plant growth would have been disturbed by less sunlight, which would have left humans and the animals they hunted with less food. Survival would have been even more difficult due to the cooling climate, particularly for populations residing in marginal environments. Once more, what appeared to be a near catastrophe was incorporated into the narrative of human adaptability and resilience. The genetic diversity that would eventually cover the entire planet was inherited by those who survived the Toba eruption. We are all quite literally descended from the people who survived that volcanic winter. Additionally, the Toba event shows how volcanic activity can affect human migration and evolution. It's possible that the eruption's disruption of the climate hastened the exodus of people from Africa as they looked for new habitats where they could survive. It's possible that the difficult circumstances also favour qualities that have come to define our species, such as collaboration, creativity, and adaptability. In innumerable ways, however, volcanoes have shaped human civilization in addition to their impact on human evolution. Ancient volcanic activity is responsible for the productivity of some of the world's most productive agricultural areas. Volcanic rock and ash form the foundations of the wine country of California, the coffee-growing regions of Central America, and the fertile soils of the Mediterranean. Because volcanic soils are abundant in the minerals and nutrients that plants require to flourish, they are incredibly fertile. Some of the most productive farmland on Earth is produced when volcanic ash decomposes over time. This explains why people have continuously opted to live close to active volcanoes throughout history, despite the clear dangers. Volcanic soils are fertile because of their distinct mineral makeup. High levels of potassium, phosphorus, and trace elements, all necessary for plant growth, can be found in fresh volcanic ash. These nutrients become accessible to plants in easily absorbed forms as the ash weathers. Weathered volcanic rock's porous structure retains moisture and allows for good drainage, which makes it the perfect material for growth. Due in large part to the extraordinary fertility of its volcanic soils, Indonesia, one of the most volcanically active regions in the world, is home to over 270 million people. More than 140 million people live in an area smaller than New York State on the island of Java alone, which is home to many active volcanoes. The breakdown of volcanic rocks and periodic ashfalls are the key to the ongoing renewal of soil fertility. In 79 AD, Mount Vesuvius famously destroyed the ancient Roman city of Pompeii. The volcanic soils surrounding Vesuvius were ideal for growing grapes, olives, and other crops, which is why Pompeii was a flourishing city prior to the eruption. The city was initially prosperous due to the same geological forces that ultimately destroyed it. Since ancient times, the agricultural prosperity of the Campania region surrounding Naples, which is home to Vesuvius, has been legendary. Roman authors extolled the region's fertility, praising farms that produced bountiful harvests and vineyards that produced superb wine. The soil's mineral and nutrient enrichment from thousands of years of volcanic activity was directly responsible for this productivity. Millions of people still live under the shadow of active volcanoes worldwide today, not because they are ignorant of the dangers, but rather because volcanic areas have special advantages that frequently exceed them. One of the world's most densely populated and volcanically active nations is Indonesia. Because of the favourable conditions for rice cultivation brought about by volcanic activity, 125 million people live on the volcanic islands of Japan. Something significant about our species is revealed by the interaction between humans and volcanoes. We excel at evaluating and controlling long-term risks in return for short-term gains. In between significant eruptions, the majority of volcanoes remain silent for decades or even centuries. Life thrives in volcanic areas during those silent times, frequently in greater quantities than elsewhere. Throughout history, human ingenuity has also been fueled by the difficulty of coexisting with volcanoes. Complex systems for tracking volcanic activity were created by ancient societies, who frequently incorporated observations of volcanic behavior into their cultural and religious rituals. For instance, many communities near Vesuvius had evacuation plans based on centuries of experience with the behavior of the volcano, and the Romans understood the link between earthquakes and volcanic eruptions. Modern volcano monitoring integrates cutting-edge scientific tools with conventional wisdom. While gas sensors track variations in volcanic emissions that may indicate an increase in activity, seismometers pick up the small earthquakes that frequently precede eruptions. Scientists can monitor surface deformation and heat changes that could be signs of rising magma using satellite imagery. Let's pause to recognize the unseen volcanic influences in your everyday existence. Deep within the Earth, volcanic heat and pressure process the materials that make up your smartphone's minerals, jewelry's gems, buildings' concrete, and windows glass. Numerous elements found in your smartphone were concentrated by volcanic processes. The metals in its circuitry, the rare earth elements in its electronic components, and even the silica in its glass screen were all formed in deep-seated magma. These materials were brought closer to the surface by volcanic activity, allowing for their extraction and refinement for human use. Due to high-temperature processes that were not possible at the Earth's surface, the aluminum found in your kitchen utensils was first concentrated in volcanic rocks. Hydrothermal fluids linked to volcanic activity were frequently responsible for the concentration of copper in electrical wiring. Volcanic gases dissolved in ancient seas may have been the source of even the salt you sprinkle on your food. Volcanic activity has even affected the water you drink. Ancient lava flows and volcanic rock formations frequently influence groundwater systems. Underground volcanic activity heats many of the world's most well-known hot springs, such as Yellowstone's geysers and Iceland's Blue Lagoon. These serve as windows into the continuous geological processes that sustain the dynamic life of our planet and are more than just tourist attractions. Some of the purest and most mineral-rich water in the world is frequently found in volcanic aquifers. Volcanic rock's porous structure makes them great natural filters, and their mineral content enriches the water with useful elements. Volcanic aquifers do offer naturally filtered water with a distinct mineral profile, and some volcanic spring waters are valued for their purported health benefits, even though many of these claims are overblown. Volcanoes and water have a relationship that goes well beyond just drinking water. The majority of the fresh water on volcanic islands, such as Hawaii, comes from rain that falls on volcanic mountains and seeps into subterranean aquifers through porous lava rock. By absorbing moisture from trade wind clouds and storing it in subterranean reservoirs, the volcanic landscape serves as a natural water collection and storage system. Speaking of Yellowstone, let's examine one of the most intriguing volcanic formations in North America. Although Yellowstone is primarily thought of as a group of hot springs and geysers, it actually sits atop one of the biggest active volcanic systems in the world. The Yellowstone caldera is roughly 34 by 45 miles in size and is occasionally referred to as a supervolcano. It's a collapsed volcanic crater with forests, rivers, and wildlife instead of a mountain. A much larger and more potent mantle plume than the one that formed the Hawaiian Islands feeds the Yellowstone volcanic system. For millions of years, the hotspot beneath Yellowstone has been active, causing the North American continent to slowly drift southwest over it, leaving a trail of volcanic features across the western United States. About 640,000 years ago, Yellowstone experienced its most recent significant eruption, which was so large that it had an impact on the climate of the entire planet. Over 240 cubic miles of material were ejected during the eruption, forming a caldera that was initially significantly larger than the one that exists today. Fossils from as far away as the Pacific Ocean and the Gulf of Mexico contain ash from this eruption. The amazing thing is that Yellowstone continues to influence the surrounding environment, even when it doesn't erupt. The park's well-known geothermal features are powered by heat from the subterranean magma chamber, which also affects local weather patterns, soil chemistry, and ecosystem dynamics. Yellowstone's geothermal features serve as a kind of sneak peek at the volcanic processes at work beneath the surface. Groundwater that circulates deeply enough to be heated by the underlying magma chamber powers Old Faithful and the other geysers in the park. The breathtaking displays that draw millions of tourists each year are produced as this water rises back to the surface. Different facets of Yellowstone's subterranean plumbing system are reflected in the various geothermal feature types, where underground water circulation causes recurring pressure buildups that cause steam and hot water to explode. Geysers are formed. Where hot water can rise to the surface more consistently, hot springs form. Fumaroles are places where volcanic gases and steam come out of the ground directly. This is an excellent illustration of how volcanoes continue to influence our world even when they are not erupting. Groundwater systems are impacted. Distinct microclimates are produced, and specialized ecosystems receive energy from the subterranean heat. In addition to providing valuable medical and industrial applications, thermophilic bacteria found in Yellowstone's hot springs have helped us understand how life might exist on other planets. Biotechnology has been transformed by the heat-loving bacteria that can be found in Yellowstone's thermal features. The polymerase chain reaction, PCR, was made possible by the enzyme Taq polymerase, which was isolated from bacteria that lived in Yellowstone's hot springs. This method is essential to contemporary molecular biology, forensic science, and medical diagnostics because it can quickly amplify tiny amounts of DNA. The remarkable stability and self-regulation of our planet is also demonstrated by the ongoing volcanic processes at Yellowstone. For hundreds of thousands of years, Yellowstone has stayed comparatively stable despite being situated on top of this enormous magma chamber. Like a massive pressure relief valve, the volcanic system gradually releases pressure through geysers and hot springs to stop more devastating eruptions. The Yellowstone magma chamber is significantly larger than previously believed, according to recent studies, but the majority of the magma is too crystallized to erupt. Instead of preparing for a significant eruption, the system seems to be cooling gradually. This implies that future volcanic activity may not be as disastrous as some widely held beliefs have indicated, but it does not rule out the possibility of such activity. Let's continue our exploration of deep time by looking at the ways that volcanic activity has shaped Earth's climate over millions of years. Volcanoes have the ability to both create and destroy climates. In addition to warming the planet by releasing greenhouse gases like carbon dioxide and water vapor, they can cool it by ejecting ash and sulfur compounds that block sunlight. The style and magnitude of volcanic eruptions have a significant impact on the climate. Global temperatures can be lowered for several years by explosive eruptions that release significant amounts of ash and sulfur compounds into the stratosphere. Global cooling, brought on by Indonesia's Mount Tambora eruption in 1815, resulted in crop failures and famine throughout the Northern Hemisphere. In some regions of North America and Europe, 1816 came to be known as the year without a summer. Sulfur dioxide, in particular, and volcanic ash combine with water vapor in the stratosphere to create microscopic sulfuric acid droplets, which causes the cooling effect. The quantity of solar energy that reaches the Earth's surface is decreased by these droplets' reflection of sunlight back into space. Until the volcanic particles eventually leave the atmosphere, the effect may last for a number of years. But not every volcanic eruption results in cooling. By releasing carbon dioxide without the short-term cooling effects of stratospheric particles, effusive eruptions, which primarily produce lava flows with comparatively little ash or sulfur, may actually be a contributing factor to global warming. The equilibrium between warming gases and cooling particles determines the overall impact on the climate. Global temperatures were significantly higher than they are today during times in Earth's history when there was a lot of volcanic activity, a phenomenon known to geologists as greenhouse climates. About 100 million years ago, during the Cretaceous period, there was a lot of volcanic activity, and temperatures were 6 to 14 degrees Fahrenheit higher than they are now. Tropical forests stretched to near polar latitudes, and the poles were free of ice caps. At other times, ice ages that lasted for thousands of years were brought on by massive eruptions. An ice age that lasted for several thousand years may have been influenced by the Toba supervolcano's eruption 74,000 years ago. According to some scientists, the glacial periods that have defined the last 2 million years of Earth's history were pushed into the climate system by volcanic cooling. But perhaps most significantly, through a process known as the carbon cycle, volcanic activity has contributed to the long-term stability of Earth's temperature. Increased rainfall accelerates the weathering of volcanic rocks, removing carbon dioxide from the atmosphere and causing the climate to cool when the planet becomes too warm. Volcanic activity rises when the planet becomes too cold, releasing more carbon dioxide and causing the planet to warm once more. For billions of years, this natural thermostat has maintained Earth's climate within a range that supports liquid water and life. Although it's a gradual process that takes thousands of millions of years to complete, it's one of the reasons that our planet has remained habitable while Venus and Mars have grown too hot and cold, respectively. Complex relationships between weathering, ocean chemistry, biological processes, and volcanic activity are all part of the carbon cycle. Weak carbonic acid, which is created when carbon dioxide dissolves in rainwater, has the ability to dissolve rocks, particularly volcanic rocks that contain calcium and magnesium silicates. Carbon dioxide from the atmosphere is eventually absorbed by this weathering process and deposited as limestone and other carbonate rocks in ocean sediments. Volcanic activity returns this carbon to the atmosphere over geological time. Volcanic eruptions heat the carbon and release it as carbon dioxide when oceanic plates carrying carbon-rich sediments subduct beneath continental plates. Over millions of years, this helps control atmospheric carbon dioxide levels and completes the carbon cycle. This process continues tonight while you sleep. Volcanic gases are being released into the atmosphere somewhere in the world. Rainfall elsewhere is carrying minerals to the sea and gradually dissolving volcanic rocks. Over geological time, these seemingly insignificant occurrences are a part of the vast, unseen machinery that maintains the suitability of our planet for life. Understanding the current state of climate change is significantly impacted by our current understanding of this carbon cycle. The long-term carbon cycle sheds light on how the Earth's climate system reacts to variations in atmospheric carbon dioxide, even though volcanic carbon dioxide emissions are far lower than human emissions in the short term. The geological record provides crucial information for comprehending how our planet might react to ongoing increases in greenhouse gas emissions, by demonstrating that warmer climates were previously caused by higher carbon dioxide levels. Now let's focus on the deep ocean, where some of the planet's most significant volcanic activity takes place far from the surface of the atmosphere. With a length of over 40,000 miles across the ocean floor, the mid-ocean ridges make up the longest mountain range on Earth. In reality, these underwater mountain ranges are volcanic chains that continuously produce new oceanic crust. Imagine this process. Magma rises from the Earth's interior and spreads out along the seafloor, forming new rock as it cools, deep beneath the ocean. Like a slow-motion conveyor belt, this new rock gradually pushes older rock away from the ridge. All of the current ocean floor was formed by this process over millions of years. Most people are unaware of the existence of the mid-ocean ridge system, despite the fact that it is one of the most volcanically active features on Earth. This is because it is concealed beneath miles of ocean water. More volcanic rock is produced annually by the ridges than by all of the land-based volcanoes put together. Volcanic activity at mid-ocean ridges produced every square inch of the ocean floor, which was subsequently gradually carried away from the ridges by seafloor spreading. One of the major findings that contributed to our current comprehension of plate tectonics was the spreading of the seafloor. The ocean floor records a history of Earth's magnetic field reversals, with parallel bands of normal and reversed magnetization spreading away from the mid-ocean ridges like a geological tape recording scientists found in the 1960s when they mapped the magnetic properties of rocks on the ocean floor. Some of the planet's most remarkable ecosystems can also be found on the mid-ocean ridges. Communities of life are sustained by hydrothermal vents along these volcanic chains, which are fueled by the chemical energy emitted by volcanic activity rather than sunlight. These underwater oases provide us with hints about what life might look like on other worlds and may be a representation of early Earth life. Our knowledge of the potential for life was completely transformed by the discovery of these deep-sea volcanic ecosystems. Scientists thought that all life ultimately relied on sunlight for photosynthesis until we discovered them. However, the organisms surrounding hydrothermal vents demonstrated that life can flourish by utilizing chemosynthesis, which obtains energy from chemical reactions rather than light. Many of the species found around hydrothermal vents are unique to the planet. These vents are home to giant tube worms without digestive systems, some of which can grow up to 8 feet in length. Rather, they are home to symbiotic bacteria that produce food from the chemicals released by the volcanic vents. While unusual fish and octopus species have adapted to the high-pressure, chemical-rich environment, ghostly white crabs scavenge around the vents. In order to draw oxygen from the chemically rich water surrounding the vents, vent crabs have developed specialized gills. In the near-freezing water, away from the heat sources, certain vent fish have evolved antifreeze proteins that stop ice crystals from forming. The octopi that live near vents have slowed their metabolisms and developed more effective respiratory systems in response to the low oxygen levels. Most astonishingly, some bacteria that live directly in the vent fluids can endure temperatures of over 250 degrees Fahrenheit, which is hot enough to instantly kill the majority of other life forms. These hyperthermophiles push the limits of what we think is feasible for biological systems and are among the most extreme life forms on Earth. Astrobiology, the study of extraterrestrial life, will be significantly impacted by these findings. Perhaps life could exist around similar features on the moons of Jupiter and Saturn, or in the subsurface oceans of other worlds, if it can flourish around volcanic vents in our deepest oceans. It is believed that Europa, one of Jupiter's moons, has an ocean beneath its icy surface. The heat produced by Jupiter's gravitational pull is probably sufficient to keep this ocean liquid, and may even fuel hydrothermal activity on Europa's ocean floor. If life is present in the oceans surrounding volcanic vents on Europa, it may resemble the chemosynthetic ecosystems that surround hydrothermal vents on Earth. These deep-sea oases are the result of volcanic processes that are also essential in controlling the chemistry of the Earth's oceans. Seawater and hot volcanic rock interact to preserve the chemical equilibrium necessary for marine life to flourish. Our oceans would eventually become too basic or too acidic for the majority of life forms if there were no continuous volcanic activity. At mid-ocean ridges, seawater experiences profound chemical changes as it flows through hot volcanic rock. The seawater is treated to remove magnesium and sulfate, and to add calcium, silica, and other metals. This procedure aids in controlling the chemical makeup of seawater and preserving the conditions necessary for marine life to form skeletons and shells. In addition to carrying heat from the Earth's interior to the oceans, the hydrothermal fluids that emerge from volcanic vents also contribute to the global circulation patterns that disperse heat throughout the planet. The intricate network of ocean currents that affect weather patterns and climate systems globally is influenced by this deep ocean heat source. We are reminded that the majority of the volcanic activity on our planet takes place in areas that are invisible to the naked eye as we investigate these underwater volcanic landscapes. Volcanic processes are continuously renewing the ocean floor, but we hardly ever give it much thought because they occur so slowly and so far away from us. However, this covert volcanic activity is essential to the functioning of our planet. I hope you'll subscribe so you can follow us on more adventures through Earth's hidden treasures if you find this exploration of our volcanic planet fascinating. Let's look at some surprising ways that volcanic activity still affects life. Recent or ongoing volcanic activity has shaped many of the most biodiverse areas on Earth. Volcanic soils enhanced by sporadic ashfalls and mineral deposits are the foundation of the tropical rainforests in Ecuador, Costa Rica, and Indonesia. These volcanic areas frequently turn into islands of evolution where rare species emerge alone. Charles Darwin developed his theory of evolution by natural selection in the Galapagos Islands, which are wholly volcanic in origin. Due to the island's remote location and varied volcanic terrain, many ecological niches were formed, allowing various species to develop special adaptations. A distinct stage of volcanic development is represented by each of the Galapagos chain's major islands. Mature ecosystems with a variety of plant communities and intricate food webs can be found on the older Western Islands. there are hints of how life spreads across newly formed volcanic landscapes on the younger eastern islands, which are still comparatively arid. On volcanic landscapes, the ecological succession process sheds light on how ecosystems evolve over time and how life bounces back from significant disruptions. Simple organisms that can survive on bare rock, such as bacteria and lichens, are typically the first to colonize an area after a volcanic eruption. These pioneer species establish the conditions for the establishment of more complex plants and animals over decades and centuries. Hawaii's volcanic landscapes provide a stunning illustration of this process. The earliest phases of ecosystem development are visible on recent lava flows. As native birds start to visit the area in search of seeds and insects, hardy ferns push through fissures in the cooling lava. These pioneering species alter the environment over time, producing shelter and soil that can be used by more complex communities. Usually, plants with long-distance travelling seeds or spores dispersed by the wind are the first to settle in newly formed lava flows. Because their spores are small and can travel great distances on air currents, ferns are especially effective pioneers. Once established, these plants start the gradual process of forming the first soil traces and breaking down rock. The growing ecosystem attracts more species as organic matter builds up from dead plants and passing animals. The pioneer plants are first consumed by insects, then by spiders and other predators. By bringing seeds into their digestive tracts, birds introduce new plant species that might not have otherwise been able to get to the remote lava flows. This ecological succession serves as a reminder that volcanic activity is essentially creative, even though it is known for causing destruction. With enough time and the correct circumstances, any volcanic landscape can eventually be transformed into a garden. Today's seemingly desolate lava fields give way to tomorrow's lush forests. Numerous variables, such as soil development, climate, and the distance from established ecosystems that can support colonizing species, affect how quickly this succession occurs. Significant vegetation can emerge in a matter of decades in tropical regions with copious rainfall, allowing succession to proceed rather quickly. The process could take centuries or even millennia in drier or colder climates. Through their impact on regional climates and weather patterns, volcanoes continue to shape our world in another intriguing way, according to modern science. By pushing air masses upward and producing rain shadows and microclimates that can last for thousands of years, large volcanic mountains produce their own weather systems. For instance, Mount Rainier in Washington state produces so much orographic precipitation that compared to areas immediately to the east, the western slopes receive over 100 inches of rain annually. With dry pine forests on one side and temperate rainforests on the other, this volcanic mountain has effectively created its own climate zone. This climate effects mechanism is elegantly straightforward. Air that is saturated with moisture is compelled to ascend when it comes into contact with a mountain barrier. The air cools as it rises, and colder air has a lower capacity to retain moisture than warmer air. On the mountain's windward slopes, the extra moisture condenses and falls as precipitation. A rain shadow desert is formed when the majority of the moisture in the air has been squeezed out by the time it reaches the leeward side. Because tall volcanic peaks represent such drastic elevation changes over relatively short distances, this orographic effect is especially noticeable. One of the most extreme examples of volcanic climate modification in North America is Mount Rainier, which rises more than 13,000 feet above the surrounding terrain. This effect is even more pronounced in the case of oceanic volcanic islands. Because of the interplay between volcanic topography and weather patterns, the Big Island of Hawaii has almost every climate zone on Earth. From tropical beaches to alpine tundra, you can experience the climate equivalent of a 2-hour drive from Hawaii to Alaska. Rich tropical rainforests are sustained by the hundreds of inches of annual rainfall that Hawaiian volcanoes receive on their windward sides. Less than 10 inches may fall on the leeward sides each year, resulting in desert conditions only a few miles away from the rainforests. Despite being in the tropics, Mauna Kea, and Mauna Loa's high elevations occasionally see snow and freezing temperatures. Human settlement and agricultural practices are both impacted by the climate changes caused by volcanoes. Nearby volcanic mountains that regulate temperatures and produce ideal precipitation patterns are responsible for the unique climates of many of the world's most important wine-growing regions. Air quality and atmospheric chemistry are also impacted by volcanic activity in the local weather. After significant eruptions, a variety of gases and particles released by volcanoes can have an impact on the local air quality for years. However, they also add healthy elements to the atmosphere, such as trace minerals that are necessary for human health and plant growth. In addition to the dramatic gases that make headlines, such as carbon dioxide and sulfur dioxide, volcanic emissions also contain trace amounts of elements that are vital to biological processes, such as fluorine, iodine, and selenium. Volcanic emissions are a significant source of these micronutrients in some places, which helps explain why plants and animals that live in volcanic regions are so healthy. It's important to take into account how these processes impact the global cycling of essential elements as we continue to examine the impact of volcanic activity. Like recycling facilities on Earth, volcanoes release materials that have been trapped in rock for millions of years back into the atmosphere, oceans, and biosphere, so that life can utilize them once more. Volcanic activity continuously releases sulfur, phosphorus, potassium, and dozens of other elements necessary for life from deep within the Earth. These essential nutrients would progressively become trapped in rocks and sediments without this constant replenishment, rendering them inaccessible to living things. For life, the sulfur cycle is especially crucial. All living things require sulfur, which is a crucial part of many proteins. Sulfur compounds are released into the atmosphere by volcanic activity, where they can travel great distances before settling in ecosystems distant from their volcanic origins. Sulfur's worldwide distribution contributes to the sustainability of ecosystems' productivity. Several timescales are involved in this recycling of elements. Plants and animals have instant access to certain volcanic gases. Others are integrated into soils and rocks, where they are gradually released over thousands of years. Others end up in deep ocean systems, where they have a long-term impact on marine chemistry. Because phosphorus is an essential component of DNA, cell membranes, and energy storage molecules like ATP, the phosphorus cycle is especially significant for life. Under typical Earth conditions, phosphorus lacks a gaseous phase, in contrast to nitrogen and carbon, which can cycle quickly through the atmosphere. One of the primary ways that phosphorus is released into ecosystems after being trapped in sedimentary rocks is through volcanic activity. Earth's biosphere would eventually run out of phosphorus and other vital elements if there were no continuous volcanic activity. As vital nutrients became unavailable, life would become more and more limited and eventually go extinct. Volcanoes are our planet's circulatory system, ensuring that vital materials continue to flow through the intricate web of life. For Earth to remain habitable, the timing of this elemental recycling is essential. The atmosphere and oceans could become poisonous to the majority of life forms if volcanic activity recycled elements too quickly. Ecosystems would become nutrient limited and ultimately collapse if they recycled them too slowly. In order to preserve the conditions necessary for complex life, the actual rate of volcanic recycling seems to be precisely balanced. Let us pause to reflect on the astounding accuracy with which Earth's habitability is preserved by volcanic processes. As carbon dioxide is progressively taken out of the atmosphere and trapped in rocks, our planet would freeze solid if there was insufficient volcanic activity. A runaway greenhouse effect from too much volcanic activity could render Earth uninhabitable. Much like Venus, Earth's volcanic activity rate appears to be precisely calibrated to sustain life-supporting conditions for billions of years. The intricate feedback systems that naturally govern the systems on our planet are to blame for this, not conscious design. The planet warms as a result of increased carbon dioxide emissions from volcanic activity. The planet cools again as a result of the increased rainfall and accelerated rock weathering brought on by this warmer climate. The opposite occurs when volcanic activity declines. Despite significant variations in solar luminosity over geological time, this natural thermostat has maintained a comparatively stable climate on Earth. Volcanic activity, weathering, ocean chemistry, and biological processes interact to form the feedback mechanisms that control Earth's climate. Scientists are still trying to fully understand the intricate relationships between these systems. The overall impact, however, is evident. Despite massive changes in the outside world, Earth has preserved conditions conducive to liquid water and life for billions of years. Considering that the sun has steadily gotten brighter over Earth's history, this stability is especially astounding. The sun was around 25% fainter than it is now 4 billion years ago. Our planet would have frozen solid early in its history and never thawed out if it weren't for the slow adjustment of Earth's atmospheric composition brought about by volcanic and other geological processes. The remarkable complexity of our planet's natural regulatory systems is demonstrated by the fact that, despite this massive shift in solar energy input, Earth has managed to maintain liquid water and temperatures that are conducive to life. A key element of this planetary scale homeostasis is volcanic activity. Although it functions on geological timescales, this natural regulation system has been in good working order for billions of years. Human activity is currently causing the atmospheric carbon dioxide to rise far more quickly than natural weathering and volcanic processes can react. We can better appreciate the stability and vulnerability of Earth's climate system when we comprehend how volcanic processes control climate over extended periods of time. Let's think about what lies ahead for our volcanically active planet as we draw to a close our exploration of volcanic deep time. Despite operating on timescales that dwarf human civilization, geological processes persist. Today, the volcanic forces that molded our planet over billions of years are still at work, forming new landscapes, recycling necessary elements, and preserving the delicate equilibrium that supports life. Volcanic activity is increasing in some parts of the world, while decreasing in others. With hundreds of active volcanoes and regular seismic activity, the ring of fire surrounding the Pacific Ocean continues to be one of the planet's most active volcanic regions. The continuous movement of tectonic plates and the flow of material deep within the Earth's mantle are reflected in this activity. About 90% of all earthquakes worldwide are caused by the Pacific Ring of Fire, which also contains roughly 75% of all active volcanoes. From New Zealand, this horseshoe-shaped region of seismic and volcanic activity extends along Asia's eastern border, across the northern Pacific to Alaska, and down the America's western coast to Chile. The Pacific region's numerous tectonic plate borders are the cause of the Ring of Fire's high level of activity. Oceanic plates melt as they move beneath continental plates, producing the magma that powers the numerous volcanoes in the ring. One of the primary mechanisms for recycling material from the Earth's surface back into the deep interior is subduction. As the underlying geological conditions shift, other areas, such as the volcanic fields of eastern Australia, are experiencing a decline in activity. Through the continuous weathering of volcanic rocks and the slow release of stored minerals, even dormant volcanic regions continue to have an impact on their surroundings. Although there isn't much activity now, the volcanic province in East Australia was active as recently as 4,000 years ago. Nonetheless, local ecosystems, agriculture, and patterns of human settlement are still influenced by the landscapes formed by previous volcanic activity. Diverse natural ecosystems and productive farmland are still supported by the fertile soils formed by ancient volcanic activity. While some volcanic features are gradually being eroded away, new ones are continually forming. The volcanic island of Surtsey is still expanding and changing after rising out of the ocean close to Iceland in 1963. The cycle of creation and destruction that has defined our planet for ages is being completed by the gradual sinking of ancient volcanic islands in other parts of the world under the waves. A unique laboratory for researching the colonization of new volcanic landscapes by life is Surtsey. From the earliest bacteria and lichens to the more recent arrival of seabirds and marine mammals, scientists have meticulously documented the introduction of new species to the island. Even in seemingly inhospitable volcanic environments, the island serves as an example of how swiftly life can seize new opportunities. Our volcanic future is made more complex by climate change. Subtle changes in precipitation and global temperature may have an impact on volcanic activity. In certain areas, melting ice sheets may change the pressure on underlying magma chambers, which could affect the patterns of eruptions. For instance, researchers in Iceland are examining the potential effects of glacier melting on volcanic activity. When ice sheets are removed, the underlying crust is subjected to tremendous pressure, which could cause magma chambers to expand and possibly accelerate eruptions. Volcanic activity and climate, however, have a complicated and poorly understood relationship. Perhaps more significant, though, is that we now have new tools to manage the opportunities and challenges that come with volcanic processes thanks to our growing understanding of them. In order to better protect human populations and provide early warning of possible eruptions, we can now monitor volcanic systems with previously unheard of precision. Numerous methods are employed by contemporary volcano monitoring networks to monitor volcanic system changes. The small earthquakes that frequently precede eruptions are picked up by seismometers. Ground deformation that could be a sign of rising magma is measured by GPS stations. Changes in volcanic emissions that may indicate an increase in activity are tracked by gas sensors. Changes in temperature on the surfaces of volcanoes are detected by thermal cameras. A worldwide perspective of volcanic activity can be obtained through satellite imagery. Additionally, geothermal power systems are teaching us how to better capture volcanic energy. Volcanic heat is already used to produce a sizable amount of electricity in nations like Iceland and New Zealand, proving that these ancient Earth processes can contribute to the sustainable power of our contemporary civilization. Utilizing the abundant volcanic heat beneath the island, geothermal energy provides about 25% of Iceland's electricity. With roughly 85% of homes heated by volcanic energy, the nation has also emerged as a leader in geothermal heating. In contrast to weather-dependent solar or wind power, this volcanic energy is clean, renewable, and always available. About 17% of New Zealand's electricity is produced using geothermal energy, and efforts are underway to increase this share. One of the world's most active volcanic zones, the Taupo volcanic zone, is home to the majority of the nation's geothermal resources. Numerous clean energy sources are produced by the same geological processes that produce volcanic hazards. Even in places without natural steam vents or hot springs, enhanced geothermal systems (EGS) technology is creating new opportunities for capturing volcanic energy. These systems create artificial hydrothermal systems that can produce electricity by injecting water into hot, dry rock that is located deep underground. The volcanic energy that lies beneath a large portion of the Earth's surface may be harnessed by this technology. Volcanic processes may become more and more entwined with the future of human civilization. Volcanic systems present both solutions and cautions as we confront the problems of climate change and the demand for clean energy. They serve as a reminder of the strength of our planet and our reliance on geological processes that have a much longer history than human history. Think about how amazing our planet is as you drift off to sleep tonight. Ancient forces are still patiently creating and renewing beneath your feet. The elements that will support future life, fill future oceans, and nourish future forests are carried by the molten rock that slowly rises from the depths. Our world was created by volcanic processes that never cease to function. They made the soil that produces your food, the water you drink, and the air you breathe. They provide the geological diversity that makes Earth such a vibrant and lovely place to live, recycle vital nutrients, and control the temperature of our planet. There are molecules that were once released from volcanic vents billions of years ago in every breath you take. At one time in Earth's history, volcanic forces processed the elements that make up your bones, blood, and DNA, calcium, iron, and phosphorus. We are literally the offspring of a restless and creative planet, formed of volcanic material. Regardless of whether your house is situated on recent sediments or old granite, the ground beneath it is ultimately supported by volcanic rock. The continents themselves are enormous collections of volcanic material that have undergone innumerable cycles of erosion, recycling, and pushing up over billions of years. Volcanic processes leave their mark on every landscape, from the deepest valleys to the tallest mountains. Volcanic activity is one of the universe's most persistent and imaginative forces, as seen in the vast tapestry of cosmic time. Earth's internal heat continues to power the processes that give our planet its unique characteristics, even as planets freeze and stars burn out. Living on a planet that is still being shaped by the same forces that created life itself, we are, in a very real sense, the offspring of volcanoes. Lava is cooling into new rock tonight, somewhere in the world, which will eventually turn into soil for forests in the future. Elsewhere, volcanic gases are adding vital elements to the atmosphere that plants will use to form new tissues. Communities of life that are unique to the universe are being sustained by hydrothermal vents deep beneath the ocean, providing tangible evidence that creation and destruction are two aspects of the same cosmic process. The ancient dance that has kept our planet alive and dynamic for billions of years is being continued far below your feet by the slow circulation of molten rock. We hardly ever notice this enormous engine of geological renewal because it runs so slowly, but it never stops. It keeps the ocean's chemical balance, controls the atmosphere's composition, and recycles the materials from continents. In the end, the tale of volcanoes is the tale of our planet's extraordinary capacity to sustain life-supporting conditions for incredibly long periods of time. The Earth's volcanic systems have persisted in their process of creation and renewal through ice ages, greenhouse periods, asteroid impacts, and mass extinctions. They have served as the backdrop for the drama of evolution, and they still sustain the amazing variety of life that gives our planet its singular character. The stability and resilience that volcanic processes have offered throughout Earth's history can be consoling as we look to the future. Long after our current civilization is extinct, the same forces that have kept our planet alive for billions of years will still be at work. The continuous creative force of our volcanic Earth will support the emergence of new species, ecosystems, and chapters in the history of life. Sweet dreams, and may your sleep be as tranquil as our volcanic planet's slow, patient work, which creates, renews, and sustains the wonder of life in our region of the universe forever. The great engines of our planet continue their age-old task of preparing the world for whatever wonders tomorrow may bring while you sleep in the peaceful hours of the night. Thank you for joining me on this journey through deep time and volcanic landscapes. Until we meet again for another exploration of our remarkable planet's hidden wonders, sleep well and dream of the creative forces that continue to shape our world. One grain of volcanic sand, one breath of volcanic gas, one beat of our planet's molten heart at a time. Now, take a moment to close your eyes and visualize yourself floating gently on a calm evening over the Mediterranean Sea. As you look down through the depths, you start to notice something remarkable in the glistening clear water below. With their surfaces covered in centuries' worth of coral and marine growth, stone columns rise from the seafloor like sleeping giants. You realize you're looking down at a whole city, perfectly preserved under the waves, as streets lined with old marble stretch into the blue-green distance. This isn't merely fantasy. Less than 5% of our planet's surface has been explored, despite the ocean covering more than 70% of it as you read these words. This implies that there are enormous underwater regions that we don't know anything about, like far-off planets, the ruins of coastal cities that flourished thousands of years ago before being seized by rising seas are hidden deep within these hidden depths. Now, let's set out on our adventure in the warm waters off the coast of Egypt, where the secrets of one of the most amazing underwater discoveries in recent memory are still being revealed. At one time, Thonis Heracleion was a thriving port city at the mouth of the Nile Delta. It was Egypt's main entry point to the Mediterranean for more than a millennium. Its harbours would receive ships from all over the known world, loaded with exotic goods, spices and gold. In its opulent temples, priests performed holy rites, and traders bargained in marketplaces where a dozen languages were spoken. However, Thonis Heracleion was even more unique because of a secret. Before the Trojan War started, it was said that the well-known Helen of Troy sought safety here with her lover Paris. In his awe-inspiring account of this city, the ancient Greek historian Herodotus said that Egyptian gods guarded foreign sailors there, and that cultures coexisted there like hues on an artist's palette. The Mediterranean then started to recover what it had given at some point in the 8th century. Buildings, harbours, and a whole way of life were all lost as the city gradually sank beneath the waves. Thonis Heracleion was reduced to a legend found in ancient texts for more than a millennium, which some academics dismissed as pure mythology. When French marine archaeologist Frank Goddio and his team made a discovery in 2000 that would change the course of history, that changed. They found enormous structures 30 feet below the surface of Abukir Bay using advanced sonar equipment. They were blown away by what they discovered. The city's streets and structures were remarkably well preserved by the mild embrace of Mediterranean waters, and it covered several square miles of seafloor. Huge statues of gods and pharaohs were lying broken but undamaged. The delicate smiles carved by ancient artists still visible on their granite faces. The crew found the remains of more than 60 ships, their wooden hulls shielded by centuries' worth of silt build-up. Most astonishingly, though, they discovered commonplace items that vividly depicted the ancient city in ways that textbooks could never. Coins found on the seafloor revealed tales of transcontinental trade routes, delicate gold ornaments that were once worn by the wives of wealthy merchants on their wrists, and necks were still found in jewellery boxes. Multiple language inscriptions found on clay tablets demonstrated a genuinely cosmopolitan society in which Greek, Phoenician, and Egyptian cultures freely coexisted. Divers started to piece together a picture of daily life in this lost world as they meticulously unearthed these treasures. The city was thoughtfully designed with broad boulevards linking temple complexes and residential areas. The biggest ships of antiquity could be accommodated by sophisticated harbour installations. While complex drainage systems kept the streets dry during seasonal floods, underground channels transported fresh water from the Nile to every neighbourhood. Archaeologists could examine building methods that had been lost to time because the preservation beneath the waves had been so thorough. They learned that Thonis Heracleion's builders had been skilled engineers who had built foundations that would endure the region's sporadic earthquakes, as well as the powerful floods of the Nile. More than 1,000 years later, during the Renaissance, the city's temples used architectural innovations that would not be seen again. Let's now cross the Mediterranean to another amazing underwater city, this one off the coast of Turkey. With its red-tiled roofs mirrored in the Mediterranean's azure waters, the ancient Greek city of Smyrna once stood majestically on the Lycian coast. Visitors can now snorkel straight over the underwater ruins at the contemporary Turkish resort of Kalaköy, looking down at the windows and doorways that once framed the everyday dramas of ancient life. Smyrna's gradual surrender to the sea is what makes it so intriguing. Smyrna's submersion occurred gradually over several centuries, in contrast to cities devastated by abrupt disasters. The locals merely relocated their residences and places of business to higher ground as the coastline changed and sea levels rose. As a result, an archaeological snapshot of an ancient city gradually bidding farewell to the land has been preserved. It feels like a dream to swim above Smyrna today. Fish now use the doorways between rooms as highways, and stone staircases lead down into the blue depths. Though they now house schools of vibrant Mediterranean fish instead of wooden sailing vessels, the ancient harbour walls remain sturdy. With its ornate Lycian tombs standing sentinel over their submerged city, the city's necropolis, carved into the rocky coastline, is still partially above water. It was unthinkable for the residents of Smyrna 2,000 years ago that tourists would one day swim through their streets while donning masks and fins. However, in certain respects, the sea has been the ideal steward of their heritage. Organic materials that would have long since decomposed on land have been preserved in the deeper waters due to the consistent temperature and oxygen deprivation. Textiles, leather goods, and even wooden beams have all survived in remarkably good condition. Our presumptions about ancient coastal life have been called into question by the discoveries made by archaeologists at Smyrna. By building underwater foundations and breakwaters that show a thorough awareness of ocean currents and wave patterns, they have discovered proof that the city's residents were highly skilled marine engineers. Knowing that their city would eventually have to face the rising sea, these ancient builders prepared with engineering solutions that contemporary coastal cities are only now starting to recognize. Off the coast of Italy, close to Naples, we come across the sunken city of Baia as we continue to explore the Mediterranean's hidden past. Previously referred to as the Roman Empire's Las Vegas, Baia served as a haven for the wealthy and influential to indulge their most extravagant fantasies. Even the notoriously indulgent Romans were scandalized by the city's reputation for decadence, its natural hot springs, and its opulent villas that dwarfed contemporary resorts. Julius Caesar, Emperor Nero, and numerous senators and patricians all kept palaces here, with heated pools, steam rooms, and intricate mosaics that portrayed scenes from everyday life and mythology. The city's thermal baths were architectural wonders. Along the coastline were private villas that competed with one another in terms of luxury and extravagance. However, Baia would ultimately fail due to its location on the volcanic Phlegraean fields, which are the same geological forces that produced its well-liked hot springs. The city gradually sank below sea level due to gradual volcanic subsidence, and by the 4th century, the majority of Baia had disappeared beneath the Bay of Naples waves. One of the most bizarre diving experiences in the world can now be found at the underwater archaeological park of Baia. The mosaic floors of former imperial palaces, which have remained intact for 16 centuries, are open for visitors to swim through. Where Roman senators once discussed matters of state, fish swim through doorways. In underwater gardens where exotic plants from all over the empire once bloomed, statues of gods and emperors stand. The exceptional preservation at Baia can be attributed in part to the water's distinct chemistry. The city structures have been preserved thanks to the minerals released by the same volcanic activity that sank it. As a result, the intricate details of Roman artistic achievement, from delicate frescoes to intricate sculptural decorations, can still be seen in this underwater museum. The most striking thing about these ruins for contemporary visitors is how human they feel. Baia preserves the private areas where people actually lived, in contrast to the monuments and temples that are usually left over from the ancient world. You can swim through gardens where lovers met in secret, past bedrooms where children were born and raised, and through private dining rooms where Roman families ate their evening meals. A child's toy boat, still positioned on what was once a terrace with a view of the bay, was one of the most poignant finds at Baia. The anaerobic conditions had preserved the wooden toy perfectly, and archaeologists could still see the small painted figures of sailors that had been meticulously placed on its deck by some Roman child. It is impossible to view such artifacts without picturing the actual inhabitants of this underwater city. The fact that many of these submerged cities were destroyed by slow changes that their residents endured and adapted to rather than by abrupt calamities makes the tale even more fascinating. According to recent studies, coastal peoples have historically developed creative solutions to deal with the rising seas, demonstrating remarkable resilience that contemporary cities are only now starting to comprehend. Ancient peoples created highly advanced early warning systems for sea level changes, according to archaeological evidence from sites throughout the Mediterranean. In order to adapt to changing coastlines, they created adaptable urban plans. They developed construction methods that would allow for partial flooding without compromising livability. Compared to many contemporary coastal communities, these ancient cities were more equipped to withstand the effects of sea level rise. Tonight, from where in the world are you listening? I occasionally ponder whether the spot where you're unwinding now could eventually serve as an archaeological site for scuba divers in the future. It serves as a sobering reminder of how fleeting human settlements are in the vast scheme of geological time. Now, let's venture outside of the Mediterranean to investigate underwater cities in other regions of the world. Sonar surveys have found what may be the remnants of a huge ancient city that covered almost 5 square miles of ocean floor in the Gulf of Cambay off the coast of India. One of the oldest urban settlements ever found. The site may be over 9,000 years old, according to carbon dating of artifacts found there. Such a discovery would have revolutionary ramifications. Historians would have to re-evaluate the chronology of human urban development if the Gulf of Cambay site were verified, as it would be several thousand years older than the oldest cities in Mesopotamia. The pottery tools and architectural fragments that have been found thus far point to a highly developed civilization that was able to plan and build extensive urban areas. The location of the Gulf of Cambay discovery is what makes it so fascinating. During the last ice age, when sea levels were significantly lower than they are now, the location would have been coastal plains. Rising waters would have gradually flooded this ancient landscape as the great ice sheets melted at the end of the Pleistocene epoch, preserving any human settlements that may have existed there. Compared to the Mediterranean, the preservation conditions in the Gulf of Cambay are very different. In addition to posing special archaeological challenges, the warmer waters and altered sediment composition have also unexpectedly preserved materials. Here, organic materials that would have long since broken down in other settings have persisted, providing fascinating insights into the everyday activities of those who lived in an era when a large portion of the planet was still covered in ice. Similar findings have been made off the coast of Japan, where structures discovered by underwater archaeological surveys are thought by some researchers to be the remnants of ancient settlements. Massive stone formations that seem to have been altered by humans make up the Yonaguni Monument, which was found off the coast of Yonaguni Island in the 1980s. These structures show how much we still don't know about our underwater heritage, even though there is ongoing discussion about whether they are man-made or natural geological formations. A particularly intriguing aspect of how ancient peoples might have adjusted to shifting sea levels has been uncovered by the Japanese discoveries. Some communities seem to have adopted amphibious lifestyles, building structures that could operate both above and below the waterline, rather than merely leaving their coastal settlements behind as the waters rose. These adaptations point to a highly developed knowledge of marine environments that we are only now starting to recognize. We start to realize that the history of human civilization is much more complicated than we first thought as we investigate these underwater cities. Despite its impressiveness, the land-based archaeological record only covers a small portion of human history. Whole chapters of our story are still hidden beneath the waves, awaiting the necessary tools and methods to properly read them. Underwater archaeology today is very different from the treasure hunts of the past. A few decades ago, the array of advanced tools used by marine archaeologists today would have seemed like science fiction. Structures hidden beneath centuries of sediment are revealed by side-scan sonar, which produces detailed maps of underwater terrain. With cameras and sampling tools that offer previously unheard-of detail about underwater locations, remotely operated vehicles can explore depths that would be hazardous or impossible for human divers. The ability to study these sites without removing artifacts from their aquatic environment is perhaps the most remarkable development in underwater excavation techniques. Archaeologists can preserve the chemical conditions that have preserved artifacts for centuries by cleaning, analysing, and recording them in underwater laboratories. Underwater archaeology presents enormous challenges. Specialised training, costly equipment, and close adherence to safety procedures are necessary when working below the surface. Storms, currents, and visibility conditions can all have an impact on excavation work, and the underwater environment can change quickly. Each dive is meticulously organised and constrained by variables such as daylight availability, water temperature, and depth. However, these difficulties have sparked advancements that are advantageous to archaeology overall. Preservation techniques for artifacts found on land have been enhanced by techniques developed for underwater excavation. Archaeologists now record and share their findings in a completely new way thanks to digital mapping and documentation techniques that were first used in marine environments. Underwater archaeology's interdisciplinary nature has brought together specialists from a wide range of disciplines, including computer science, engineering, geology, and marine biology. The application of artificial intelligence to the analysis of underwater archaeological data has been one of the most exciting developments in recent years. Potential archaeological sites can be found across large swathes of the ocean floor with the aid of machine learning algorithms, which can spot patterns in sonar data that the human eye might overlook. In order to identify and catalogue artifacts, AI systems can also analyse underwater photos. This helps archaeologists concentrate their efforts on the most promising finds and expedites the documentation process. Underwater archaeological sites are far more common than previously thought, according to these technological advancements. The puzzle of human coastal history is completed each year by the discovery of new submerged settlements, harbours, and individual structures. Many of these sites require sophisticated robotic systems to access because they're situated in regions that are now too deep for conventional diving. Researchers are still in awe of the preservation of organic materials in submerged environments. Remains of wood, leather, textiles, and even food can endure for millennia in the frigid, oxygen-poor conditions of deeper waters. Since organic materials usually decompose in decades or centuries, these materials offer insights into ancient daily life that are rarely available from land-based archaeological sites. Ancient ship cargoes with their contents intact have been found recently, offering in-depth glimpses into historical trade networks. Because amphorae containing grain, wine, and olive oil have been discovered with their original contents intact, scientists can now examine ancient agricultural and culinary practices in previously unheard-of detail. Direct communication from people who lived thousands of years ago is possible thanks to the survival of wooden writing tablets with readable inscriptions. The personal belongings that have survived underwater, jewellery, toys, tools, and household items that relate to the common human experiences of play, work, love, and everyday survival, may be the most poignant. These relics serve as a reminder that the inhabitants of these now demolished cities were not all that dissimilar from us. They enjoyed small pleasures, took pride in their work, and worried about their families. We come across evidence of how ancient peoples perceived and engaged with marine environments as we continue to explore these underwater worlds. Cities along the coast were not merely constructed next to the sea, they were closely related to it. Advanced understanding of tides, currents, and seasonal weather patterns can be seen in harbour installations. The ability of ancient engineers to construct structures that could withstand storm surges and wave action is demonstrated by underwater foundations. Numerous ancient coastal peoples engaged in aquaculture, managing marine resources using methods that contemporary environmental scientists are rediscovering, according to archaeological evidence. Shellfish beds, fish pens, and artificial reefs demonstrate that these communities considered themselves to be stewards of marine ecosystems rather than merely consumers of coastal resources. In these ancient cities, the land-sea relationship was dynamic and fluid. Above and below the waterline, many settlements had buildings that performed several purposes. During storms, harbours served as flood control systems. Seasonal variations in water levels were taken into consideration when designing waterfront structures. In times of flood or high tide, streets and plazas could serve as canals. For contemporary coastal communities dealing with rising sea levels and intensifying storms, this adaptability offers important lessons. Successful coastal cities had to cooperate with natural systems rather than fight them, as ancient urban planners recognized. They created communities that were flexible enough to adapt to change without losing their core capabilities. Living in these amphibious cities had significant social repercussions. This dual relationship was reflected in the distinctive cultures of communities that relied on both land and the sea. Religious rituals combined elements of the land and the sea. Both fields served as inspiration for art and architecture. The ongoing interaction between land and water that characterized day-to-day existence was reflected even in language and poetry. These coastal peoples may have developed extraordinarily advanced knowledge of oceanography and marine biology, according to archaeological evidence. They were able to navigate using stars and currents, forecast weather patterns, and spot minor changes in marine ecosystems that pointed to more significant environmental changes. Through religious ceremonies, practical customs, and oral traditions, this knowledge was transmitted from one generation to the next. Coastal peoples were carrying out complex scientific observations thousands of years ago, as evidenced by the discovery of ancient astronomical instruments and tide prediction devices at underwater locations. They were creating mathematical models to forecast marine conditions, mapping tidal cycles, and monitoring seasonal variations. They were engaging in early oceanography and marine science practices in many respects. We discover evidence of vast trade networks that linked far-flung coastal communities as we dig deeper into these underwater archives. Underwater site artifacts demonstrate that people, products, and ideas traveled across entire ocean basins on intricate maritime routes. By uniting communities over great distances through a common maritime culture, these historic trade networks served as the cornerstone of the first genuinely global economy. The ships themselves, which have been conserved in underwater archaeological sites, provide amazing insights into the technology of ancient seafaring. Thousands of years ago, shipwrights created advanced methods for creating ships that could survive lengthy ocean journeys. They had a unique understanding of cargo management, sail configuration, and hull design that would not be fully recognized until the age of exploration. Ancient ships were frequently far bigger and more advanced than previously thought, according to recent discoveries. Across thousands of miles of open ocean, some of the ships discovered in underwater archaeological sites could transport hundreds of tons of cargo. These were advanced ocean-going ships built for deep water travel, not rudimentary boats that clung to coastlines. These ancient ships' navigational aids reveal a remarkable level of astronomical and mathematical knowledge. Ancient mariners were able to use star sightings and mathematical calculations to determine their position, as demonstrated by celestial navigation devices. Early knowledge of magnetic navigation is revealed by devices that resemble compass needles. Wooden or metal-carved charts and maps demonstrate a thorough understanding of the hazards, currents, and coastal features. Most intriguingly, there is evidence of early forms of marine archaeology at some underwater archaeological sites. Underwater structures and artifacts pique the interest of ancient peoples who occasionally purposefully salvaged materials from older submerged sites. This points to a historical awareness that valued conserving and researching the artifacts of past societies. The intriguing tale of these underwater cities is further complicated by their religious and spiritual significance. Many ancient cultures thought that even after cities vanished under the waves, they still had spiritual significance. Pilgrims continued to visit sacred sites, diving or sailing over them to offer sacrifices and ask for divine favor. Some underwater sites continued to receive ritual attention for centuries after they were submerged, according to archaeological evidence. Even though these locations could no longer be reached on foot, votive offerings have been discovered strewn throughout submerged temples and sacred areas, suggesting that people still regarded these locations as spiritually active. Accurate historical and geographical details about actual locations that had been lost to the sea were frequently preserved in the mythology surrounding sunken cities. It is now acknowledged that stories that were written off as pure fiction by previous academics can provide important hints about the locations and features of real archaeological sites. It turns out that historical memory can be remarkably effectively preserved over millennia through folklore and legend. Because of this recognition, archaeologists are now more attentive to local legends and traditional stories when looking for underwater sites. Oral histories from indigenous communities frequently contain comprehensive details about submerged landmarks and coastal changes. For contemporary archaeological research, these traditional knowledge systems offer priceless direction. One of the most beneficial trends in modern underwater archaeology is the cooperative relationship between traditional knowledge keepers and archaeologists. In-depth knowledge of underwater landscapes that are invisible to outside researchers is frequently possessed by communities that have preserved ties to ancestral coastal territories. Archaeological research has become more efficient and respectful as a result of this partnership approach. As our technology develops, we are learning that there is a lot more human history on the ocean floors than anyone had previously thought. Every new excavation reveals artifacts that deepen our understanding of ancient coastal life, and every new survey identifies new sites. Investigating these underwater archives is essentially rewriting the history of humanity. The ramifications go well beyond history and archaeology. Addressing contemporary climate challenges requires an understanding of how ancient coastal communities adjusted to environmental change. Time-tested solutions are provided by traditional building methods, urban planning approaches, and resource management systems which contemporary communities can enhance and modify. Unprecedented opportunities for scientific analysis are being created by the preservation of organic materials in underwater locations. New details about ancient populations' health, diets, and migrations are being revealed by ancient DNA recovered from underwater archaeological contexts. Underwater environmental samples offer comprehensive documentation of past ocean chemistry, ecosystem shifts, and climate conditions. Ancient coastal environments and their historical changes are being depicted in ever more detailed detail by these scientific analyses. Today, we can trace the development of marine ecosystems, reconstruct historical weather patterns, and comprehend the effects of human activity on coastal environments from thousands of years ago. Important baseline information for comprehending contemporary environmental changes is provided by this environmental archaeology. Deep historical roots of environmental consciousness are also being revealed by the study of underwater cities. In order to manage marine resources sustainably, ancient coastal peoples created complex systems. They comprehended ideas that contemporary environmental science is rediscovering and improving, such as carrying capacity, seasonal constraints, and ecosystem management. According to archaeological evidence, prosperous ancient coastal communities followed what are now considered to be the earliest examples of ecosystem-based management. They created social institutions that could impose conservation measures over whole regions, rotated harvesting areas to allow for recovery, and preserved reserves of important species. Spiritual and cultural elements that supported sustainable practices were frequently included in these antiquated conservation systems. Seasons when certain species should not be harvested were designated by religious ceremonies. Important habitats were shielded by cultural taboos. Social hierarchies made sure that people who had a long-term interest in the survival of the community made decisions about resource management. Sobering lessons about the vulnerability of sustainable resource use are provided by the disintegration of these traditional management systems, which frequently resulted from outside forces or environmental changes. Archaeological sequences demonstrate how, when their established systems were upset, communities that had been effectively managing marine resources for centuries could disintegrate in a single generation. However, the same archaeological record also shows how adaptable and resilient humans can be. Communities frequently relocated and rebuilt their civilizations elsewhere after losing their original coastal territories to rising seas. While adjusting to new surroundings, they preserved their cultural identities. They developed fresh approaches to altered situations while maintaining fundamental knowledge and procedures. For contemporary coastal communities dealing with comparable difficulties, this resiliency offers hope. Humans have successfully adapted to significant environmental changes numerous times throughout history, according to the archaeological record. As we confront the coastal challenges of the 21st century, we can draw from vast reservoirs of knowledge and experience. It's important to consider the implications of these discoveries for our comprehension of human civilization as we draw to a close our exploration of these underwater cities. It is obvious that the conventional view of human progress as a gradual transition from prehistoric to advanced societies needs to be revised. Advanced civilizations with knowledge and skills we're only now starting to comprehend are revealed by the underwater archaeological record. These ancient cities were more than just forerunners of contemporary communities. They stand for different ways of living in cities that have been especially tailored to coastal and marine settings. Their approaches to resource management, storm protection, and sea level change were frequently more advanced and long-lasting than those taken by contemporary cities. Ancient peoples were far more skilled engineers and scientists than previously thought, as evidenced by the technological advancements found at underwater archaeological sites. They created construction methods, navigational aids, and environmental control systems that are competitive with their contemporary counterparts. Their solutions were sometimes better than the ones being used now. Most significantly, these underwater cities serve as a reminder of the transience of human settlements and the importance of long-term planning in urban design. The same environmental issues that destroyed these ancient settlements will eventually affect every city we construct today. The archaeological record offers examples of effective adaptation techniques, as well as cautions about the negative effects of inadequate adaptation. New facets of these extinct civilizations are constantly being discovered through the continuous investigation of underwater archaeological sites. Every diving season yields new findings that deepen our knowledge of prehistoric coastal life. 10 years ago, it would have been impossible to study these sites in the ways that are now possible thanks to advanced technology, and future developments will surely uncover even more about these underwater worlds. Due to the collaborative nature of contemporary underwater archaeology, these findings gain from a variety of viewpoints and levels of experience. Understanding the impact of underwater environments on archaeological preservation is aided by marine biologists. Engineers provide insights into both contemporary excavation techniques and traditional building methods. New tools for evaluating and disseminating archaeological data are created by computer scientists. The cultural significance of underwater discoveries is interpreted by art historians. The intricacy of the underwater archaeological record and the variety of ways these finds advance human understanding are reflected in this interdisciplinary approach. In addition to being archaeological wonders, the ancient cities that lie beneath our oceans serve as reminders of the extraordinary adaptability of our species, windows into alternate human society structures, and sources of useful advice for tackling contemporary issues. Tonight, as you drift off to sleep, you might have a dream in which you're floating above one of these underwater cities, gazing down through pristine water at streets where people used to walk, houses where families used to reside, and harbours where ships used to deliver news from far-off places. These are not merely remnants of a vanished era. Rather, they are proof of the ongoing human narrative that binds ancient coastal inhabitants to contemporary societies that are still learning how to coexist with the ocean. Although the ocean is good at keeping secrets, these submerged civilizations' mysteries are still being revealed by diligent research and developing technology. Every new finding broadens our knowledge of human resourcefulness, adaptability, and the timeless connection between land and sea that has molded our species over time. The past is still very much alive and well in these peaceful depths, where coral grows on temple walls and fish swim through old doorways, ready to impart knowledge to us that we are only now starting to understand. There is no real loss of the ancient cities that lie beneath the sea. They are merely waiting for us to gain the wisdom, to hear their voices through the ages, communicating to us through ruins and artifacts about the ageless human experience of living by a sea that is constantly changing. The speed at which the technology enabling these discoveries is developing is astounding. By looking for underwater anomalies in satellite imagery, artificial intelligence is now assisting archaeologists in locating possible sites. Large volumes of sonar data can be processed by machine learning algorithms, which can then identify patterns that point to man-made structures hidden beneath sediment and marine growth layers. Now, autonomous underwater vehicles that are outfitted with high-resolution cameras and sampling gear are able to explore environments and depths that are unattainable for human divers. Working non-stop, these robotic explorers map underwater environments with greater accuracy than is feasible from the surface. They can carefully record locations that might take human teams years to thoroughly survey by staying underwater for weeks at a time. These cutting-edge systems are gathering data to build intricate three-dimensional models of underwater archaeological sites. Researchers can now explore ancient cities without ever getting wet, thanks to virtual reality technology, looking at architectural details and spatial relationships that would be challenging to appreciate during actual dives, in ways that would not be feasible in the real underwater environment. These digital reconstructions are also opening up underwater archaeological sites to the general public. Virtual underwater archaeology experiences, which allow visitors to explore these submerged cities from the comfort of dry land, are starting to be incorporated into museums all over the world. Through interactive displays, visitors can explore construction details, interact with virtual artifacts, and gain insight into the daily routines of ancient coastal peoples. Underwater archaeology is now accessible to audiences who might not otherwise have the chance to visit real underwater sites thanks to these educational technologies. Conservation science as a whole has been transformed by the preservation methods created for underwater archaeological materials. Innovations in chemical treatment, environmental control, and long-term storage techniques have been prompted by the particular difficulties of conserving artifacts that have been submerged for centuries. Archaeological materials recovered from underwater sites are not the only ones that benefit from these developments. It is now feasible to perform in-depth stratigraphic analysis beneath the waves thanks to recent advancements in underwater excavation techniques. In order to read the environmental and cultural history preserved in these sedimentary sequences, archaeologists can now examine the layered deposits that build up over time in underwater sites. Instead of viewing these ancient cities as static snapshots, this temporal resolution enables researchers to comprehend how they changed and evolved over time. Underwater archaeology's interdisciplinary nature has given rise to new academic disciplines that integrate computer modeling, marine science, engineering, and conventional archaeological techniques. The study of geoarchaeology looks at how human settlements were impacted by changes in coastal environments over time. Ancient ocean conditions and marine ecosystems are recreated through marine paleoecology. The enormous volumes of data produced by underwater archaeological projects are analysed and interpreted using computational techniques in digital humanities approaches. Because underwater archaeological sites frequently cross national borders or are located in international waters, international cooperation has become crucial. UNESCO's conventions on underwater cultural heritage offer frameworks for cooperative research and protection of these sites. Researchers from several nations collaborate on joint expeditions, exchanging resources and knowledge while honouring each nation's claims to its cultural heritage. As new sites are found and new technologies are developed, the ethical and legal aspects of underwater archaeology keep changing. Archaeologists, governments, and local peoples must continue to discuss issues such as who owns underwater cultural heritage, how to safeguard sites from damage and looting, and how to share discoveries with descendant communities. Understanding how ancient coastal peoples reacted to previous episodes of climate change and sea level fluctuation is the subject of some of the most fascinating current research. Evidence of how these communities modified their building methods, resource management plans, and settlement patterns in response to shifting environmental conditions is preserved in the archaeological record. This information is directly applicable to contemporary coastal communities dealing with comparable issues. Ancient harbour technology research has uncovered complex engineering solutions that contemporary port designers are starting to recognise and use. Compared to their contemporary counterparts, ancient breakwaters, quays, and channel management systems frequently used more resilient and sustainable principles. Ancient underwater archaeological finds are now used as inspiration for some modern coastal protection projects. Ancient shipwrecks preserved in underwater archaeological settings offer unmatched insights into past maritime networks and technologies. Complete ships with their goods still inside provide comprehensive knowledge about historical maritime trade, navigation, and cross-cultural interactions. While cargo contents reveal trade relationships spanning great distances, ship construction wood can be used to pinpoint the location of vessels. Ancient lighthouses, navigational aids, and coastal markers have recently been found in underwater locations, demonstrating the advanced maritime infrastructure that underpinned prehistoric networks of trade and communication. These facilities, which used sophisticated knowledge of optics, structural engineering, and coastal dynamics to safely guide ships through hazardous waters, were frequently engineering marvels in their own right. Complex political and economic systems that coordinated activities across land and sea are revealed by the social organization needed to establish and sustain these coastal cities. Administrative records retrieved from submerged locations demonstrate how ancient bureaucracies oversaw everything from tide tables to harbour fees. Direct proof of business ties between remote communities can be found in trade contracts written on materials that survived underwater submersion. Ancient coastal peoples created complex risk management and insurance systems for maritime trade, according to archaeological evidence from underwater sites. Common commercial practices across large geographic areas are indicated by standardized weights and measures discovered at several underwater sites. Ancient maritime economies were far more integrated and complex than previously thought, as evidenced by the existence of banking and credit systems. Rich traditions of literature and art with a maritime influence can be found in the artistic and cultural artifacts retrieved from underwater archaeological sites. Submerged city mosaics, sculptures, and ornamental items frequently have oceanic imagery and marine themes. Shipboard musical instruments demonstrate how cultural customs were adjusted for maritime life. Religious artifacts show how spiritual beliefs combined elements of the land and the sea. Evidence of highly developed systems for knowledge transmission and preservation can be found in the discovery of ancient libraries and educational facilities in underwater locations. Direct access to ancient scientific, literary, and practical knowledge is provided by the survival of waterlogged but readable texts under conditions that would have destroyed them on land. Our perception of earlier intellectual accomplishments is being literally rewritten by these discoveries. Evidence of early experimental science and technology development has been found at a few underwater archaeological sites. Coastal peoples were actively creating new technologies to address real-world issues, as evidenced by the prototypes of navigational instruments, architectural innovations, and marine engineering solutions. There are striking parallels between these historical research and development endeavors and contemporary scientific methodologies. Important information about historical ocean conditions, climatic trends, and ecosystem shifts can be gleaned from the environmental data conserved in underwater archaeological contexts. Pollen, marine life, and chemical signatures found in sediment cores from archaeological sites help to reconstruct the ancient environmental conditions in remarkably detailed ways. Scientists are better able to comprehend the natural variability in ocean and climate systems thanks to this paleo-environmental data. Sophisticated knowledge of marine nutrition and food preservation methods is revealed by the analysis of ancient dietary remains from underwater sites. Modern nutritionists and food scientists are very interested in learning from the ways that ancient coastal populations processed, stored, and prepared seafood. Certain conventional preservation methods are turning out to be more successful than contemporary industrial ones. Traditional maritime medicine systems are supported by the discovery of antiquated medical texts and pharmaceutical materials at underwater locations. Ancient seafarers acquired specialized knowledge about how to treat illnesses and injuries that frequently arose during lengthy ocean voyages. Modern medical researchers are looking into some of these traditional remedies for possible therapeutic uses. Evidence of prehistoric environmental monitoring and prediction systems has been found during recent underwater excavations. People who lived along the coast evolved complex techniques for monitoring seasonal variations, forecasting weather patterns, and foreseeing natural disasters like storms and tsunamis. Astronomical observations, biological indicators, and subtle environmental cues that contemporary science is only now starting to recognize were frequently included in these traditional forecasting systems. Ancient coastal cities' social structures frequently included distinctive features tailored to maritime life. Underwater site evidence indicates that these communities created specialized legal frameworks to settle conflicts involving fishing rights, maritime trade, and the management of coastal resources. Modern approaches to ocean governance are still shaped by these ancient legal traditions, which also had an impact on later maritime law. Ancient coastal peoples maintained vast communication networks that connected far-flung communities through frequent maritime contact, according to archaeological evidence. Coordinated activities across entire ocean basins are demonstrated by the use of standardized symbols, navigation aids, and message systems at various underwater locations. Ancient globalization processes that linked disparate cultures via common maritime experiences were built on these communication networks. Ancient coastal life's religious and ceremonial elements frequently focused on the interaction between human societies and marine habitats. Evidence of complex rituals intended to guarantee safe travel, good weather, and a wealth of marine resources has been found at underwater archaeological sites. These rituals demonstrated an advanced knowledge of marine ecology, tidal patterns, and seasonal cycles. Evidence of old scientific instruments and observational facilities that are as sophisticated as contemporary oceanographic equipment can be found at some underwater locations. Ancient coastal peoples made systematic scientific observations of marine environments, as evidenced by tidal prediction devices, modern measurement tools, and weather monitoring systems. Everything from agricultural planning to navigation decisions was influenced by the information they gathered. Ancient maps and charts that accurately depict coastlines, ocean depths, and navigational hazards over large areas have been found at underwater sites, revealing intricate geographical knowledge. The mathematical and surveying abilities displayed in these cartographic accomplishments would not be seen in European traditions for many centuries. Certain ancient maps depict geographical relationships and features that have only lately been verified by contemporary satellite imagery. Evidence of complex ancient engineering projects that significantly altered coastal environments is still being found by archaeological excavations at underwater locations. The capabilities of harbour construction, channel dredging, and coastal protection projects are comparable to those of contemporary marine engineering projects. Sustainable methods that cooperated with, rather than opposed, natural processes were frequently used in these antiquated infrastructure projects. Unprecedented insights into ancient maritime fashion and functional clothing design can be gained from textile, and clothing remains preserved in underwater archaeological contexts. Features that contemporary outdoor clothing designers are rediscovering and adapting were incorporated into specialized clothing created for life at sea. Advanced knowledge of human factors in marine environments is demonstrated by weather-resistant construction methods, waterproof materials, and clothing systems made for abrupt climate changes. Specialized industries that grew up around maritime activities have been revealed by recent underwater site discoveries of ancient workshops and manufacturing facilities. Facilities for building ships, workshops for making sails, and centers for producing rope demonstrate how coastal communities established whole industries focused on assisting with maritime endeavors. These sectors frequently use methods and materials that contemporary manufacturers are researching for possible use. Materials recovered from underwater sites are starting to shed light on the educational systems that underpinned ancient maritime cultures. The practical knowledge of navigation, seamanship, and marine science was passed down from generation to generation through training manuals, educational tools, and test materials. Contemporary maritime education programs are starting to take inspiration from these antiquated teaching methods. Every new finding deepens and complicates our understanding of ancient coastal civilizations as we continue to delve into these underwater archives of human history. These communities' advanced technologies, environmentally friendly behaviors, and flexible approaches provide important insights for contemporary societies dealing with comparable environmental issues. The patient accumulation of knowledge that these discoveries represent is reflected in the patience needed for underwater archaeological work. The enormous puzzle of human coastal history is completed with each artifact that is painstakingly removed from its underwater resting place. Every location that has been mapped and recorded retains priceless knowledge about how our ancestors perceived and engaged with marine environments. As you rest comfortably tonight, remember that patient archaeologists and their robotic helpers are still working slowly on the process of discovery somewhere beneath the world's oceans. Ancient cities wait patiently in the deep sea's gentle darkness, as they have for centuries, ready to reveal their secrets to anyone who approaches them with the appropriate deference and scientific curiosity. There is much more human history hidden in the ocean that covers the majority of our planet than we have yet to uncover. Every rising and falling tide traverses areas where people once lived, loved, worked, and dreamed of unimaginable futures. The cities that lie beneath the waves are not abandoned societies. Rather, they are patient educators who are ready to impart knowledge about adaptability, resiliency, and the enduring bond between people and the sea. Sweet dreams, and may you sleep as soundly under the soft embrace of the ocean's ever-changing tides as these ancient cities did.